are going to discuss derivatives. We're going to discuss integrals throughout this whole year, but without the understanding or basic understanding of functions this year, we can't do anything. So really the first thing we need to establish this trimester is what the heck is a function, okay? Now you guys, other classes, you've talked about the definition of a function before. Do they recall that definition? In mathematics, a function is?
It's a statement that doesn't allow, I'm not going to say this in like mathy terms or terms that would be either correct, but like when plotted along a graph, it wouldn't, lines wouldn't be over each other on the y-axis. So like that one right there.
One I've sketched over there on the right?
Yeah.
Why is that a function?
Because they don't overlay on the y-axis.
Okay. Anybody recall what test function has to pass?
Vertical line.
You've got to pass a vertical line test, meaning that for every x value, there can only be at most what?
One y.
One y value, yep. And we'll look at the definitions down here real quickly in a second. But the question is, how is a function today described and how is it used in real life situations? And exactly, we've had dealings with functions before. So our goals today is to make sure we either revisit or at the end of the day understand what a function is, okay? We want to understand if real life situations are functions. We want to be able to define domain and range of a function. You've done that before, but things are going to get a little different. Things are going to get a little more interesting with this here. And then understand direct and inverse proportionality, okay? So I like to start out each lesson by making sure we understand the vocabulary that we're going to be using throughout the section. And the first one here is function, okay? Volunteer to read that for me?
A function is a process or relation that associates each element x of a set x, the domain of the function, to a single element y of another set y, possibly the same set. The codomain.
Codomain, yep. It's called the codomain of the function. Okay, here's the deal. There's a lot of wordiness up here. The way I like to read this is the following. The domain and the range are all going to be parts of each other, but this is how I like to say this. This is a big time definition for simply saying for each, whoops, hang on a second, let me get the right tool up here. This is a big long definition really for saying for each x or for each input, x values are always inputs in the function. For each x, there exists at most one y value or an output. It's kind of like saying this. Belle, how old are you right now at this exact time? How many years? Is it possible that right now at this exact time that Belle could be 16 and 74 years old at the same exact time? It's like saying for this one particular time right now, Belle is 16 and 74. Does that make any sense?
How fourth dimensional is she then?
I don't know. I don't know if you can really say that you're the same or different ages within the fourth dimension because time is measurable, right? So that's one of those deals where it's just not going to work. Now, if I would say this, right now at this exact moment, Belle is 16, would that be okay to say that? Yeah, because for that one particular time, she's one particular age, okay? I played in one basketball game. Stat book said I had 32 points and 98 points. Does that make sense? No, I should have one value for the number of points that I scored in that game, okay? So for each x, the input, there exists at most one y value for an output. That's what that really means. Domain right here, guys. The domain is the set of all x values. It's the x values of a function. Take a look over here in this example. It says here is a graph of, I can't read it very well up here, but on your notes it says y equals what? Okay. Put a little arrow on this right here, kids. Okay, that graph, put a little arrow on it. Y is equal to the square root of x plus 4. The question says, what's the domain? In other words, in that graph, which x values are covered? What's the far left x value that's hit there? -4. So all the x values covered are x greater than or equal to what value, kids? -4. How come -5 isn't hit over here? Why isn't -5 part of the domain? Say that again, Colton. Yeah, it starts at -4. We can't have -5 because this would become y equals the square root of -5 plus 4. Guys, what is -5 plus 4? Can I root negative values? I could, they'd be imaginary, but we don't talk about imaginary values in terms of domain and range, so that's why this would start at -4. That's where it starts, so good. All right, so if domain covers the x values, how far left and right my graph goes, what's the range going to cover? Range would cover the, not x values, but the y values of a function. And same graph right here. I can't read this up here because it's pretty small, but I know you have it in your notes. It says for the function y equals the square root of x plus 4, we notice that the curve is either on or above the horizontal axis. No matter what value of x we put in, we're always above the x-axis. So we say that the range in this case is, what's your lowest point on this in terms of a y value, kids? 0. And it's 0 and everything. If I continue to go onward, this is going to continue to increase. So what's the range on that then, kids? Well, it says the range is all y values greater than or equal to what? Exactly. It's right there. Okay? So the domain covers all x values of the graphed function. The range is going to cover all y values of the function. You just need to figure out what they are. Okay? And then a concept that's going to come up a lot today is about proportionality and how we write functions when we're given a statement. Guys, we say y is what here? Directly proportional to x if there is a constant k such that what, kids?
Y equals kx.
So you might see something like this. Y equals, I don't know, let's just pick on 20 today. 20x. Okay, that's an example of an equation that's directly proportional. An example might be the amount of money I make in a day is equal to $20 per hour times the number of hours I work. Okay? That might be an example. But in this form right here, this is something that's directly proportional. On the next page, you might have something here that looks like, I don't know. Not directly proportional, but inversely proportional. When we say y is inversely proportional to x if there is a constant k such that y is not equal to k times x, but rather what?
K divided by x.
Yes. Today when I drove to work, I drove the law-abiding speed of 55 miles per hour. So my speed is equal to 55 miles over a certain number of hours. So would you guys agree that speed is equal to a distance divided by time?
I can agree.
So I would say that my speed is inversely proportional to the amount of time I travel, because it's a distance divided by time. Okay? So an example might be this. I don't know. I might say my speed 55 miles per hour, or my speed s is equal to my distance traveled divided by what? Okay? That's an example of something that's inversely proportional. Inversely proportional means there's some kind of constant up top here, and it takes on the form y is equal to kx. Again, k is just some what? K is always going to be some number. Anytime you hear me talk constant in here, that's just going to be some number. We don't know what that constant is, but it's going to be some number. Okay? So kids, a lot of the terms that are there, refer to them, look them up if you need to. We should be in good shape there. Okay? Here we go. Example 1, determining if data is a function. Determine if the following tables represent a function or not. We need to do some labeling down here. You ready for that? I have two tables down here, time distance table. Go ahead and call the times an x value, or my inputs and my outputs. Got a question for you. They're going to ask you what table represents a function. In other words, for the x values that are listed, which x values have one output? Well, take a look at this first table. If I input 0, what am I going to get out every single time?
0.
If I input 1, what do I get out?
40.
Is that okay? Yeah. What if you input 2, what do you get out?
40.
And that's okay. Every time I input 2, I should get what out?
40.
I input 3, what do I get out?
40.
I input 4, what do I get out?
20.
And if I input 5, what do I get out?
0.
So all these x's, they don't, there's nothing here that matches here. So this is saying for every x over here, there's only one value it kicks out. So for every input over here, there's only how many outputs? 1, okay? There's a problem in this table right here. Anybody recognize it right away? Say it again, Colton. Exactly. Guys, right here, if you notice, the first time we dumped 3 into this function, when we input 3 right here, what did it kick out?
54.
Which by definition of a function mathematically says that every time I input 3, I better get out what?
54.
Well, when I input 3 again, the same exact 3, what did it kick out this time?
84.
That's like saying, I don't know, if you work 3 hours, you get $54. If you work 3 hours, you get $84. That doesn't make any sense. We're the same person. We work the same amount of time. We shouldn't get 2 different pays. You're only going to get 1 different pay. Which of the following tables represents a function and which one doesn't?
The force. Something force.
So the first one is a function. This one over here is not a function because f of 3 the first time was equal to what? What was f of 3 equal to the first time, kids?
84.
And then the second time, if it was a function, f of 3 should equal 54 again, but f of 3 the second time was equal to 84. Therefore, that table is not representative of a function. It's saying that, guys, for that x value of 3, there's not one output. There are actually how many outputs for that one input of 3? Well,
12.
there's 2 of them, aren't there? When I input 3, how many outputs did I get out? 2 of them, okay? No problem. Questions on what a function is and what a function isn't? Graphically, I just sketched this up here. Val, you said which test does it have to pass to be?
Vertical line.
Is this one passing?
Yeah.
How about this one? Does that pass a vertical line test? Not a situation where that would be a function, okay? All right, guys, let's talk finding domain and range. Let's do this. Let's call this maybe, I don't know, let's go 16 over 25x squared. That's what should have been up there in the notes that didn't transfer over from the Google Doc to Word document. Kids, we're asked to find domain and range of a function. And a lot of the courses you've taken in the past, the domain has typically been the set of all real numbers. But we have to ask ourselves today this. When we're dealing with domain, this is what I tell kids to do all the time. When you're ever dealing with a domain, always ask yourself, ask if x cannot be something. And when I say this, kids, we always want to get real values out. When I input a real value, I want to get the output of a real value. So for instance, problems arise mathematically when we end up with 0 in the what, kids? We say it's all fun and games until somebody divides by what?
0.
Exactly. So some of the situations that present itself are the following. You might be able to put a certain x value into a denominator that makes the denominator of some division problem equal to 0. Okay? Another situation that causes domain issues is, well, square roots that are what kind of a number? Are square roots of negative numbers real numbers or imaginary numbers, guys? In order to be a function, we only want to deal with the real number set. So there might be situations where there's certain x values that give you the square root of a negative number. Now when I ask you guys to find the domain of this function right up here, 16 over 25 minus x squared, is there anything that x cannot equal? Or is there any x value that would give us a problem right there or allow us not to get a value out? 16 over 25 minus x squared. Anytime you see a fraction like that, are there any x values that would produce 0 in the denominator?
Well, 5 mainly.
5, anything else?
0.
-5 mainly.
Okay, 5 and -5 would make 0, right? Because if I throw 5 in for x right here, what's 5 squared, kids?
25.
So 25 minus 25 would be 0. And this would become 16 divided by 0, which is,
It's undefined.
it's undefined. It's not good. Also, -5 squared, what is that, kids?
25.
Okay, so the domain for this, kids, going to be all real numbers except what values? All reals except plus or minus 5. Because if I throw 5 in for x or -5 in for x, what's that make your denominator again, kids? What's that make your denominator? 0. Is 0 in the denominator a good thing or a bad thing? Okay, now the range on this, I worry about the range, but here's the range on this. First thing I'll tell you to do, when you're dealing with range, especially with functions that are going to be a little trickier here, you might want to use Desmos for this. So we're going to jump into Desmos together. I'm going to head over here. Guys, in Desmos, our function of, what's it say, 16 over 25 minus x squared. Let me throw that in there quickly, okay? Okay, so we're going to go 25 divided by, what was it again? 16 minus x squared, is that right, guys?
It was 16 on the numerator.
Oh, 16 up top, all right. Y equals 16 divided by 25 minus x squared. Let me blow this up a little bit. Kids, I'm going to put a couple lines in here. X equal 5. Okay, I put x equal 5 and x equal -5 in there for a reason. Why would I do that?
Those are where the asymptotes?
Yeah, those would be considered vertical asymptotes right here. Basically, these would be the x values that made the denominator what? Made the denominator 0. So this graph right here, guys, is the following. What's going on right here is this. If I zoom out a little bit, maybe one more. What happens is this red graph right here in this bottom right, this is not crossing over the blue line, and it's also not crossing over the what? Looks like it's right on the x-axis, doesn't it? But it's really not going to here, because here's the deal. When you graph this, this is just going to get closer and closer and closer to 0. It's just never ever going to get there, okay? Same thing over here. Never going to get there. Now the domain, all real values, I can go everywhere left and right except where this green line is and where this blue line is, and that happens at what x values? What x values did that happen at, guys?
5, -1.
Okay, I put those in there to say our graphs aren't going to cross over those. Now, when we talk about range right here, we got to break this up into two parts. I have a part that's below the y-axis, so it looks like everything here, I go home again, looks like everything here is going to continue to go on forever and then just get closer and closer to that line. So it looks like I'm going to have y values less than what for sure here? Looks like we have y values less than what for our range? You're all right. If these two red parts down here below the x-axis are always going to be below the x-axis, the y value is going to be, for range, less than or equal to what? What's the y value at the x-axis, kids? 0. Okay, we're going to have a range that's y less than or equal to 0. Now, the part right here that's tricky is this. Guys, what's the lowest point on this up here?
Approximately 0.064.
And that 0.64 is really coming from 16 divided by 25 there. So you've got to kind of look at decimals and say, okay, looks like I'm going to have y values for my domain, for my range everywhere less than 0, because this is just going to get closer and closer to the x-axis but never cross. I've got everything from 0 and down, but I also have everything from 0.64 and what, kids? Up. Okay, so decimals is going to aid you in this. And what I would put down here for my domain is the following. I'm going to say we have y values in a graph that are going to be less than 0. That was everything below the x-axis. And we're also going to have y values greater than or equal to, what was that decimal value there again, kids? Yeah, 0.64 right here again. Okay? So everything above or equal to 0.64 is going to be your range. Okay? So guys, when you're doing domain, ask if x can't be something. Does x cause problems like 0 in a denominator or get you a negative root? And then when you get to range, I think you should use what? Decimals to determine what y values are going to be covered and not covered, okay? All right, questions on the second page at all? Give me some sort of sign you're alive right now. All good? Okay, next page. Here we go. Very top here, kids. Oh, I like this problem. We're going to apply a domain and range. Now, guys, when we start applying domain and range, you got to understand there's a difference between domain and range for a given function. But you also got to understand there's a difference for a domain and range when we're talking about a real-life application. And this example is pretty cool. It says a cricket's chirp rate C equals f of t as a function of the temperature T in what?
Degrees Fahrenheit.
Degrees Fahrenheit. This function is given by C equals 4T minus 160. Now it says the following. Knowing that the highest ever recorded temperature in the world is 134.1 degrees Fahrenheit, what's the domain and the range of this situation? Okay. What's C represent again, kids?
Cricket chirp.
Chirp rate. And what's T represent again?
Temperature outside.
Okay. I'm just going to throw this up here for a second. I'm going to jump into decimals. First of all, 4T minus 160. What kind of graph is that going to be?
Directly proportional.
It is. But it's also going to be linear, right? Isn't that kind of like in slope-intercept form? Okay, guys, I've got kind of a sketch of a graph up here, okay? Now, guys, think about crickets. crickets chirp rate. Seems like the warmer it gets outside, you might hear a cricket chirping. But what happens to the number of chirps that they make as it seems to warm up outside in the summertime or the springtime? Become more per minute or less per minute?
More.
More. And then the colder and colder. Do you guys go outside at night right now? Do you hear any crickets typically this time of year? Okay, this formula is kind of talking about that. Now guys, is it possible that a cricket could have a negative chirp rate? Okay, so the question becomes then this. At what temperature here is their chirp rate going to be 0? According to this formula. What temperature is it outside where their chirp rate is 0? How much? 40 degrees. And then what was the highest temperature ever known for us? 134 degrees. So really, we probably need to look at this function from how many degrees outside? This formula says at 40 degrees, you're going to get how many chirps? 0. I don't want to go left of this because this is saying the chirp rate now is what type of a value down here? 0. It's negative. It's going to be below 0. It's negative. So that doesn't make any sense. There's no way that something can have a negative chirp rate. Okay? So what we're saying is we're going to look at this window from 40 up to, what was the highest temperature ever recorded? 134.1, is that right? Okay, so here's what I'm going to go ahead and do. I'm going to go ahead and put a vertical line in at 134.1. So watch what I do here. I'm going to type in x equal 134.1, and I'm going to find my intersection. We're basically going from this point to this point. Kids, I have a question. This is the part of the graph that we're looking at. I'm not going to go above 134.1 because, well, we don't know what happens beyond that. Okay, it's never been that warm. Guys, what would the domain of this real application look like here? From what to what? What are the x values we're covering? 40 to 134.1. How about the range on this? From what to what?
0 to 376.4.
Yep. Okay, does that make sense? Again, I don't want to go below 40 degrees because by this graph or by this function that they give you, they're kind of saying if you get colder than 40 degrees, you're going to have negative chirps. Guess what, kids? You know what the temperature is outside right now? 49 degrees. If it stayed 49 degrees, would you expect to hear some chirps tonight? According to this model? Some, and probably a lot or a little. Okay, and then the warmer it got, we should go outside and wait till it turns 40 degrees and see if we hear any, see if this is true or not. Who's with me tonight? We'll sit outside, wait for 40 degrees, and at 40 degrees we better hear no crickets, because if we hear a cricket, we're going to write this book publisher and say, shame on you. Anybody want to do that with me tonight? Sound like fun?
If I could fit into my schedule, I would.
Okay, settle down with the excitement, okay? You don't want to do that tonight? All right, you get the idea here. So guys, from this graph, what was the domain again? Let me grab my marker here. What was the domain again from where to where? 42. Okay, so I'm going to write my domain up like this. My domain is going to be all x values from 40 up to 134.1. Okay, and then range simply going to be, what were our temperatures or our chirp rates? 0 up to, what was that high value again? 376.4. So again, I get that this is a linear function, could have gone forever, but we've got to kind of look at this within the context of what's really happening here in this situation. So I get that this is linear, I get that this is increasing everywhere, I get that every x value would work in here to make this a function, I get that there's an input, and I get that there's always an output, but the thing we need to consider is, within real life, what do we have to consider, okay? And in this case, at 40 degrees is when your chirp rate gets down to 0, and the highest ever recorded temperature is as high as we can go, because we don't really know what happens after that. And that gives us that high value on the range of 376.4 chirps per minute, right? So anytime you're looking at domain and range within mathematical context or real life context, you've got to understand the difference between the two before you go ahead and apply a domain and range to that. All right, last example here. Let's write some functions. This is pretty simple. Writing functions involving proportionality, okay? The cost of steak is directly proportional to its weight in pounds. It says the cost is how much, kids? $8.99 per pound. We need to come up with a function to model this, okay? Is this inversely proportional or directly proportional? And I'm going to let my cost be y, and I'm going to let the number of pounds be x. If the cost is directly proportional to the weight in pounds, and each pound is $8.99 per pound, what's the function going to look like for this, kids? 8.99 times what? Well, 8.99 times x. Y equals 8.99 times x. Right? It says the density of an object, so I'm going to let my density be y. The density of an object is, are we directly proportional or inversely proportional here? In this next one. What's it say? Inversely proportional to its volume, I'll call x. It says assume the mass or the constant k is how many kilograms, kids? Well, it'd be 68 kilograms. This is like our constant that they're giving you, okay? How do you write a function that represents this situation if the density is inversely proportional to the volume? What would you write? Say it louder. Yep. Okay, and you guys have talked about density is equal to mass over volume in science at some point, haven't you? Y is equal to 68 over x. You got it. Okay. Guys, notes-wise, questions on what we covered so far? Good. Okay, let's see if we've got this. Hang on a second. This is weird to be recording.